We have seen that when heat is transferred to an object, the motion of the particles making up the object becomes more vigorous and its temperature rises. But we are left with some questions. How much does the temperature of a substance change with a given input of heat? Is the change in temperature the same for all substances? Is all of that heat energy going into just raising the temperature of a substance? Now let's see if we can deduce the answers to those questions. You may recall that when you eat a piece of hot pizza, the roof of your mouth becomes burned, but your tongue doesn't. The reason isn't because the cheese is at a higher temperature than the crust. As you can see, the temperature of both the cheese and the crust are the same. Then what is going on? As we previously learned, when objects at different temperatures are brought together, heat is transferred from the higher temperature object to the lower temperature object. If energy is conserved, then the total heat transferred from the hotter object must equal the total heat transferred to the cooler object. What might you think the amount of heat energy, Q, that is required to change the temperature of a substance is related to? Correct. Q is proportional to the mass of the object, m, and, of course, the change in temperature, delta T. By including a constant, C, the equation can be made specific to a substance. The constant, C, is known as the specific heat, and is a measure of the heat required to change the temperature of a particular mass of a substance by a particular temperature. The SI unit for specific heat is joules per kilogram Kelvin, but other commonly used units include joules per kilogram degree Celsius and calories per gram degree Celsius. Water has one of the highest specific heats of any substance. That is why it's used for heat storage in solar panels and as a coolant in automobile engines. Now getting back to that pizza. Now can you guess why the cheese burns your mouth but the crust doesn't? Cheese has a higher effective specific heat. The cheese contains more water and has a specific heat of about 3.5 to 4 joules per kilogram degree Celsius, whereas the crust is mostly starch with a specific heat of 2.5 to 3 joules per kilogram degree Celsius. Therefore, the cheese gives up more heat energy to your mouth as it cools to body temperature. Not convinced? Then try eating a piece of pizza upside down next time. Experiments involving heat flow are normally carried out in a device known as a calorimeter, which thermally isolates the experiment from its surroundings. The calorimeter usually measures a temperature change in the system caused by the experiment. From our own personal calorimetry experiments, we know it is not wise to drink hot liquids from a metal cup. Let's illustrate the point. Suppose you take 300 grams of tea at a temperature of 95 degrees Celsius and pour it into a steel mug at 20 degrees Celsius, having a mass of 125 grams. Assuming no energy is lost to the surroundings and that the tea is essentially water, what will be the final temperature of the mug when it reaches thermal equilibrium with the tea? First, apply the conservation of energy. What is the total change in energy of the system? It must be 0. So, we set the sum of the individual Q's equal to 0. Make substitutions for the Q's using the specific heat equations. Now, using the given values for the specific heats of water and the metal mug, what is the final temperature of the tea and mug? Correct. It's 91.8 degrees Celsius. Why did the tea cool down so little and the mug heat up so much? Because the specific heat and mass of the tea are higher than those for the mug. It is important to remember that for equal masses and inputs of heat, the specific heat and temperature change are inversely related. Have you ever wondered why those blue ice packs are so good at keeping the food in your ice chest cold? Have you ever wondered where hurricanes get their energy? Probably not at the same time. Yet the answer to both questions is the same. It's latent heat. Remember that matter typically occurs in three phases: solid, liquid, and gas. We can illustrate this point with water, which can exist as solid water ice, liquid water, and gaseous water vapor. Now let's try a little experiment. Take a piece of ice out of a freezer that is at -10 degrees Celsius and place it in a beaker at room temperature. We know that the ice will begin to heat up, but how will the temperature increase with regard to the heat input? Correct. It will increase linearly. Eventually, the ice begins to melt at 0 degrees Celsius. What happens to the temperature of the ice-water mixture as heat is added and the ice continues to melt? Correct. The temperature doesn't rise, but remains around 0 degrees Celsius. Why does the temperature of the ice-water mixture remain constant? Because the input heat energy is being used to produce the phase change, rather than to increase the temperature. The heat involved in a phase change is called latent heat. For a solid-liquid phase change, it is known as the latent heat of fusion. After the ice completely melts, what do you think happens to the temperature of the resulting liquid water? Correct. The temperature will start to increase again. When the temperature of the liquid water reaches its boiling point at 100 degrees Celsius, another phase change occurs, from liquid water to water vapor. The temperature stops rising and remains around 100 degrees Celsius during the phase transition. The latent heat of the liquid-gas phase change is known as a latent heat of vaporization. What do you think also affects the total amount of heat released during a phase change, besides the latent heat term? Correct. It's the mass of the substance undergoing the phase change. Therefore, the heat, Q, involved with the phase change is simply given by the mass times latent heat. The SI units for latent heat are joules per kilogram, but another commonly used unit is kilocalories per kilogram. Now we understand why latent heat was the answer to our earlier questions. The blue ice absorbs considerable heat energy in the ice chest, while maintaining a constant cold temperature due to its latent heat of fusion. When water vapor in a hurricane condenses as rain, considerable energy is released due to the latent heat of vaporization. This energy then drives the intense winds of the storm. Now let's put to use what we have learned. We'll start with an insulated cup containing 100 grams of water at 20 degrees Celsius. Next, we'll add 10.0 grams of water from an ice-water mixture. What is the final temperature of the mixture? It's 18.2 degrees Celsius. Now we will again start with 100 grams of water at 20 degrees Celsius in an insulated cup. But this time we will add 10.0 grams of ice from an ice-water mixture. What is the final temperature of the mixture? It's 10.9 degrees Celsius. In this case, the extra heat energy needed to melt the ice caused the final temperature of the mixture to be much lower. Now we know why adding ice is a good way to cool a drink.